Power in an AC circuit and the power factor. We have seen that a voltage V equals Vm sin omega t applied to a series RLC circuit drives a current in the circuit given by I equals Im sin omega t plus phi, where Im is Vm by Z and tan phi is Xc minus XL divided by R. Power is the product of current and electric potential, that is, Im sin omega t into Vm sin omega t plus phi. Now multiplying and dividing this equation by 2 and writing sin omega t into sin omega t plus phi as cos phi minus cos 2 omega t plus phi. We get Vm Im by 2 into cos phi minus cos 2 omega t plus phi. Now the average power over a cycle is given by the average of the two terms in RHS of the above equation. It is only the second term which is time dependent. Its average is 0 because the positive half of the cosine cancels the negative half. Therefore, we get average power as Vm by root 2 into Im by root 2 into cos phi, which can be written as Vi cos phi. Now again, this can be written as I square Z into cos phi. So, the average power dissipated depends not only on the voltage and current but also on the cosine of the phase angle phi between them. The quantity cos phi is called the power factor. Special cases for the power factor cos phi. Case 1. Resistive circuit. Case 2. Purely inductive or capacitive circuit. Case 3. LCR series circuit. Case 4. Power dissipated at resonance in LCR circuit. Click on the buttons to know more about them. Resistive circuit. If the circuit contains only pure R, it is called resistive. In that case, phi equals 0, cos phi equals 1. There is maximum power dissipation. Purely inductive or capacitive circuit. If the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos phi equals 0 and no power is dissipated even though a current is flowing in the circuit. This current is sometimes referred to as a weightless current. LCR series circuit. In an LCR series circuit, power dissipated is given by the equation P equals I square Z cos phi, where phi equals tan inverse Xc minus XL divided by R. So, phi may be non-zero in a RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. Power dissipated at resonance in LCR circuit. At resonance, Xc minus XL equals 0 and phi equals 0. Therefore, cos phi equals 1 and P equals I square Z equals I square R. That is, maximum power is dissipated in a circuit through resistance R at resonance. Concepts. A. For circuits used for transporting electric power, a low power factor implies large power loss in transmission. Explain. B. power factor can often be improved by the use of a capacitor of appropriate capacitance in the circuit. Explain. Answers. A. We know that P equals IV cos phi, where cos phi is the power factor. To supply a given power at a given voltage, if cos phi is small, we have to increase current accordingly. But this will lead to large power loss I square R in transmission. B. Suppose in a circuit current I lags the voltage by an angle phi. Then power factor cos phi equals R by Z. We can improve the power factor which is tending to 1 by making Z tend to R. Let us understand with the help of a phasor diagram as shown how this can be achieved. Let us resolve I into two components, IP along the applied voltage V and IQ perpendicular to the applied voltage. IQ is called the wattless component, since corresponding to this component of current there is no power loss. IP is known as the power component because it is in phase with the voltage and corresponds to power loss in the circuit. It's clear from this analysis that if we want to improve power factor, we must completely neutralize the lagging wattless current IQ by an equal leading wattless current I-Q. This can be done by connecting a capacitor of appropriate value in parallel so that IQ and I-Q cancel each other and P is effectively IP into V. Example. A sinusoidal voltage of peak value 283 volts and frequency 50 Hz is applied to a series LCR circuit in which R equals 3 ohms, L equals 25.48 millihenry and C equals 796 microfarad. Then find A. The impedance of the circuit, B. The phase difference between the voltage across the source and the current, C. The power dissipated in the circuit and D. The power factor. Solution. A. To find the impedance of the circuit, we first calculate XL and XC. XL is given by 2 pi nu L. Putting the given values, we get its value as 8 ohms and XC, which is 1 by 2 pi nu C, is given by 4 ohms. Therefore, Z equals 5 ohms. B. Phase difference. Phi equals tan inverse XC minus XL divided by R. Comes out as minus 53.1 degrees. Since phi is negative, the current in the circuit lags the voltage across the source. B. The power dissipated in the circuit is I square R. Now I equals Im by root 2, which comes out as 40 amperes. Therefore, power loss equals 4800 watts. D. Power factor cos phi is cos 53.1 degrees, which is equal to 0.6. Concept. At an airport, a person is made to walk through the doorway of a metal detector for security reasons. If she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does this detector work? Answer. The metal detector works on the principle of resonance in AC circuits. When you walk through a metal detector, you are in fact walking through a coil of many turns. The coil is connected to a capacitor tuned so that the circuit is in resonance. When you walk through with metal in your pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. This change in current is detected and the electronic circuitry causes a sound to be emitted as an alarm.